All right. Good day, everyone. Hope you guys have been having a good NDC, good conference so far. Before I get started, just a quick show of hands. How many of you have got the bulk of your production workloads running on the cloud right now? All right, cool. And what about your running in your own data center? How many of you got majority of your stuff running in your own data center? All right, cool. All right, not bad. Probably a bit of half and half. My name is Mahesh Krishnan. I work for a company called AGL Energy. It's based in Melbourne, Australia. And yeah, so that's right. So I've come all the way here to do a talk. It's a long way to fly. It's a long flight. AGL Energy, obviously, we are in the energy business. We not only generate electricity, we also we also sell gas and electricity to consumers in Australia. And we run a lot of our infrastructure, a lot of stuff in the cloud. Probably, I would say that we're probably one of the largest consumers of Azure within Australia itself, one of the largest consumers. We run things like our SAP workloads and everything else in there. I have been working in the cloud from the very early days of Azure. I've been an Azure MVP for a number of years. And I've been very passionate about building highly resilient applications that run on the cloud. So when you run your applications, in terms of when it fails, it doesn't really affect the application. The application continues to run and things like that, even in the event of failure. The talk I'm going to give today is titled Architectural Patterns for the Cloud. But the interesting thing is that whether you're running your applications in the cloud or it's a distributed applications running in your own data center, you will find that all the patterns that I talk about is still relevant to you. However, as you'll see during the talk, it becomes even more relevant if you're running in the cloud. The agenda is actually pretty simple. I'm going to talk about some of the guiding principles based on which the catalog of patterns I've picked up are. And I'll run through a series of patterns. There are about 21 patterns that I'm going to talk about today, right? So the emphasis is more on breadth rather than on depth of the pattern. So in each and every pattern, I'll talk about what is the problem that's actually trying to solve, how do you actually fix the problem, how do you solve the problem, and then some considerations. So hopefully it gives you enough to make you dangerous, right? So hopefully, when you go back to work and then you come up across a scenario where you need to use these patterns, you'll dig a little bit deeper and then start utilizing these patterns itself. So as I said, there are 21 patterns. So I would suggest that you hold on to your questions till the very end, so I run through my presentation, run through it. And I'll wrap up with a few links that you can actually use when I said deep dive. So you can actually follow those links and get more information about these patterns itself. So let's talk about some of these guiding principles. What is the reason that most people move to the cloud? And the primary reason a lot of people cite is the power of, to leverage the power of the seemingly infinite cloud, right? So you run your workload, and if you want to scale, you have lots of people visiting your site and things like that, you can quickly scale up, scale out, whatever you want to call it, quite easily without having to worry about running out of hardware and so on. So I said seemingly infinite because sometimes you can actually run out of space even over there, right? But to do that, a lot of cloud providers, there are certain things that come out of the box, right? So you can run multiple instances, and they'll give you load balances, global load balances that will allow you to distribute your traffic equally between all the instances and so on and so forth. But you still need to make sure that you architect your applications appropriately to make use of this, the scale that it actually provides. So if you've got a big monolithic application, you need to break it down into smaller components, and you need to start to decouple these components. And once you decouple these components, then it makes a lot more sense. You can start to scale these things independently. You can start to isolate them, and if some of these things fail, they don't start to affect other parts of the system itself. So that's one of the things that you need to start thinking about. The second reason that people want to move to the cloud is that it's a lot cheaper than the average data center that you run your current workloads on. And the reason it's cheap is because the cloud is literally built on commodity hardware that's a lot cheaper than the expensive ones that you put into your racks in your data center. So they are more prone to failure than the hardware over there. So they even talk about things like mean time to recovery. That's more important than the mean time to failure, which is what a lot of these hardware typically state in their specifications and so on. So that's the first thing. And the second thing is, of course, the cloud is massively multi-tenanted, right? So you're running a lot of other people are sharing the infrastructure, sharing the same resources that your applications are running on. So you could have, your application could be really well written, behaving really well, but you could have noisy neighbors who literally spoiling the party that you're actually having, right? So they start to eat up into your resources and so on and cause failure. So that's another reason for failure. And again, you've got distributed applications. So when you have distributed applications, chances are some of the downstream services, they have actually failed. And so what does that mean to you, right? So you have no control over these applications that they've failed. So the basic thing here is that failure is imminent, right, in the cloud. And rather than avoid failure, you've got to start to embrace failure. And you start thinking about, I spoke about how you start to put things into components and so on. So when failure does happen, you want to make sure that you have a limited blast radius, so it doesn't affect some of these other services and so on. That's going to be one of the key things that we want to explore. And when failure does occur, you want to make sure that you degrade gracefully as well. So that's another key thing that you want to think about. Never send a human to do a machine's job. This is one of the quotes from The Matrix. It's one of my favorite movies. And it's very appropriate to use it now. And when we are deploying our applications and so on, there used to be a time when we would have a planned outage. You say, well, we've got a window of about 2 hours, and you kind of like give your build scripts to deployment scripts to someone, and they would actually go ahead and deploy it. Click ops, do a bunch of things to deploy the application, and if it succeeds, it's good, but if it fails, then it takes a lot more time to kind of like roll it back. You can't do those things anymore, right? So you want to have automation. You want to automate everything. So not only do you want to automate your build pipeline and everything else, your whole deployment needs to be automated. You want to have zero downtime deployment. We're all talking about high availability, and you can only do that when you're automating all those things. But it doesn't stop there. It just doesn't stop when you deployed your application. You want to make sure that nothing goes wrong over there. You want to have good monitoring over there and good alerting. So when something actually goes wrong or is about to go wrong, you are notified. You're alerted that something is going to go wrong. And then you can do something about it. Oh, but wait, why do you need to do something about it, right? So again, there's a human over there. So what you need to do is to make sure that the machine takes control of that as well. So you have a whole bunch of self-healing and everything else built in. All of that is automated as well. You want to build for performance and responsiveness. In this day and age where the span of attention of people is very, very short, even a few milliseconds can cause people to be impatient and then go over to another site. And there's a loss of sale and everything else. All the statistics will show that you can actually map on how slow the response is and how it starts to affect sales and things like that. So, but certain things just do take a lot of time to do. So how do you actually solve this problem? And you do this by running things asynchronously. So the customer still gets a good experience, but you can actually take a lot of the work offline and do these things asynchronously. The other thing is that you want to start to optimize for speed. While I did computer science in university, we were taught about things like how you need to optimize for storage space and things like that. You talk about things like databases and normalization and so on and so forth. But now storage is cheap. You can create multiple copies of your data, store it in different places, and that makes if it makes your machine go faster, your application go faster, so be it. And I put a little asterisk over there, right? So it's still kind of like it depends on the situation. You don't want to be in a situation where you're just ridiculously creating more and more things and you're blowing out your costs. So you still need to keep an eye on it. But in most cases, that should be fine. And again, you want to start thinking about latency and bandwidth. If you are running, in the old days, like client-server applications, the client and the server, they all were in the same network. And you could have really chatty calls, going back and forth between your client and your server, and it was all okay. But now in a distributed environment, when you have like your services, your API sitting somewhere else and your data sitting somewhere else, some of these high chattiness can actually kill your application. They can make it so slow that it's totally unusable. So when you're designing these things, you want to start thinking about those things as well. Last but not the least, you also need to deal with legacy applications. I mean, AGL, we run a lot of SAP workloads and so on. And again, we have a lot of modern applications, and so you still have your legacy applications like SAP, and you have your modern applications, your web apps, your APIs and microservices and everything that you've built, and they still need to communicate with each other. And not only that, in some cases, some of the workloads reside in your like on-prem, while your modern applications are sitting in the cloud. So you need to start thinking about that as well. So we'll talk about some of these patterns that addresses a lot of these things, how you deal with things like legacy applications and your modern applications. And so I've categorized the patterns that we want to talk about into 5 separate areas. We'll talk about availability patterns. What happens when, how do you make your application highly available, even in the event of failure and so on? Data management patterns. You have a lot of, these days, data is cheap and storage is cheap, and we end up producing more and more data. So we'll look at some of the patterns to deal with some of those things. We'll look at design and implementation patterns. I did talk about things like legacy applications talking to your cloud applications. We'll look at some of those patterns that'll address that. We'll talk about performance and scalability patterns as well. And then finally, we'll finish up with resiliency patterns. How do you deal with failure? When things go wrong, how does the application deal with it? So let's start with availability patterns, right? I mean, we talk about things like high availability. You want to make sure that the application is running all the time. And you can achieve a lot of these things quite easily, right? I mean, there are certain things that you can get out of the box with all the cloud providers. You can run multiple instances, like I said earlier, and you can put set a load balancer in front of it. And if you're using databases, you can have replication. You can create multiple copies of your data, and you kind of like get some level of high availability. But that's not enough in most cases. So there are 3 patterns that I want to talk about. The first one is your health endpoint monitoring. So when we talk about SLAs and things like that, one of the key things, the problem that we want to fix is that there's a need to ensure that applications are running within the required SLAs. So how do you address this thing? What you do is you build functionality within the application itself that starts to check the health of the application. And then you expose this through endpoints. And so an agent sits over there, and then it kind of like hits these endpoints frequently to see what the status of the application is, and starts to monitor it. Now, there are certain things that you want to think about when you're building your health endpoint itself. First and foremost, do you start to expose like just one endpoint that goes in and checks all the different things and all the downstream services that it actually connects to? Or you kind of like have multiple endpoints that can actually, for each and every one of those functionality, right? Do you want to do like a shallow health check or a deep health check? A shallow health check could be like a simple ping, right? So whether the service is up and running. A deep one could be looking at all these other services that it actually talks to, and then sees whether they are up and running as well. You want to start thinking about the frequency in which you actually want to do your health check. How many pings do you do? I mean, you don't want to be in a situation where you're constantly hitting your health service endpoint and you're kind of like DOSing yourself, right? So you want to avoid things like that. You have an agent that's monitoring it. What if the agent actually goes down? So who monitors the monitor, right? So those are additional things that you want to think about. The next pattern I want to talk about is around this pattern called load leveling using queues. And one thing that I did mention is that there are certain things that are just slow. It takes a lot of time to execute, right? So when you have let's say you have an endpoint, like an API endpoint, and your client talks to it, let's assume that it takes a long time to finish the operation that it wants to do. So literally what happens is when it hits the endpoint, it's just waiting for this thing to finish up. And when it's waiting, it just holds up valuable resources. And then when you have heavy load, and a lot of these threads are actually waiting, that starts to create problems. Performance and reliability problems actually start to come up. So how do you actually solve the problem? Well, you solve the problem by actually having a queue and doing a lot of these things asynchronously. Now, I'd like to kind of like explain this with as a non-technical example, right? Let's say you want to go and apply for a permit. So you go to your council, you're making some changes to your house, and you go to the council, and you submit a form. So they've got a window over there, and a person sitting over there, and you can actually go and submit the form, right? It's fine. So you go and submit the form. It takes the person some amount of time to process the form and get back to you. And while it's happening, all you're doing is waiting over there, right? So it's a waste of resources on your part to just sit over there, stand over there, waiting for the other person to complete it. And then someone else comes along, and they want to apply a permit. Because you're holding it up, right, and all he needs to do is get in line. And now he's waiting even longer. And then another person comes in, and suddenly you have like lots of people waiting. And until my job is done, theirs cannot be processed, right? So what if they actually turn it around a little bit, and then they have like a tray right in front of it? All you need to do is to go and drop your item in the tray, and you can actually go away, right? So your time is not wasted. And everyone who actually comes in can actually drop their forms, and they can go on their merry way as well. And you think about it, right? So you can also do this thing even when the council is not open. So the tray is sitting just outside the window. So you can actually use the same analogy in this scenario, right? So what actually happens is, oops, go too far. So what happens is that the client calls the API endpoint. The API endpoints whatever task it needs to do, it's a long-running task, it creates an item and it puts it into a queue. A worker thread over here, a command processor, picks up this item and then processes it offline, asynchronously. It can take a long time to do it, that's fine. It does this stuff, it writes to a database and so on and so forth, it's all fine. If there's a number of items in the queue actually increase, you can actually start to scale this. You can actually have more processes that are doing it. Same analogy, if I extend the analogy. If there are lots and lots of application forms sitting over there, I can have another person start to process some of those forms as well, right? So in this scenario, what actually happens is that if for these are durable queues, if something actually goes wrong, I keep hitting the wrong button. If something actually goes wrong over here, and there's a failure, the item goes back into the queue and you can actually execute it over and over again. So you've got to be careful so that you can actually start to think about things like idempotency over here. What it means is that when you're executing the same task again, you want to get exactly the same result. Let's say you are doing like a wire transfer, right? And you're halfway through the wire transfer and there's a failure and the whole system breaks down. So what happens is the item goes back into the queue, and if you execute the same item again, you don't want to deduct money from the same account twice, right? This is where you need to be careful and you need to think about idempotency. Going back to the council example, right? So let's assume that there are hundreds of forms that get delivered to the council every day, but whatever reason you didn't do yours on time, but you're prepared to pay extra, right? So you want to pay $100 to make sure that yours is done quicker. The council will happily take your money and process yours first, right? So that's probably a separate tray for that, where you can actually pay. So the same thing applies over here. You can actually start to set up priority queues. And based on the priority queues, you can actually start to pick the ones that are more important and then process them ahead of time. So you can actually have a whole bunch of queues over here. And then depending on the function that you want, you can post to the right queue. And the command processor can actually pick it up and then execute it. And of course, the command processor can be scaled independently. So you see more and more items queuing up over here. You can actually start to scale it. So all those items get done quickly. But every now and then, in spite of doing things asynchronously, there will be a lot of load on your server. And there will be a point where you have so much load that it's starting to cause performance and reliability issues. So how do you actually fix this, right? So what you need to do is you kind of like start to monitor your resource utilization. And when your resource utilization, you start to set some thresholds. And when it reaches those thresholds, what you want to do is, firstly, what you want to do is you want to disable some of those non-essential services so you can actually free up some resources within your server. And then you've got to start rejecting new requests that are coming in. There's no two ways about it. You start to reject those requests. Because it is more important that your service doesn't fail than rejecting some new requests that are coming in. And then you do other things, like you start to defer some of the non-essential tasks as well. But the key thing to keep in mind over here is that throttling is always a temporary measure. So what you do is you start to reject the new requests that are coming in, but while you're rejecting it, you want to make sure that you put other things in place. So like things like auto scaling or things to make sure that you can start to process more requests and things like that. Once you do that, then you can actually get rid of the throttling itself. You also need to keep in mind that when something actually goes wrong and you're rejecting these calls, you are returning the appropriate code back to the calling client. One of the patterns I'll talk about is the retry pattern, right? What the retry pattern is, when something actually goes wrong, we basically say, hey, maybe it's a transient error, just try again, right? You don't want to be in a scenario where you are experiencing a lot of load and you're rejecting the service, and the client actually thinks, oh, it's temporary, I'm going to call this person again, call the service again, and it starts to compound the problem as well. So making sure that you return the appropriate codes, the client can basically look at it and go like, okay, well, there's something wrong with it. I will hold back for a while before I try my operation again. And you also need to think about how you perform graceful degradation. When some of the throttling and things like that happen, how does the client handle? So these are things that you need to think up front before you start the whole application, the architecture itself. Well then, let's talk about data management patterns. Like I said, in this day and age, we are generating lots and lots of data, right? Data is king. And even if we don't need the data, we just collect it anyway so that we can maybe use it in the future, which is okay. There's nothing wrong with it, right? But with it come a lot of other problems that we need to deal with. So I've got about 6 patterns over here: cache aside, materialized view, CQRs, VALET key, and I'll go through them one by one, starting with the cache aside pattern. Now, caching is actually a really good thing. When it helps with performance, rather than go to the data source every time, the cache is a lot faster than, let's say, a relational database. So you go to it, get the data, and you return back the data back to the client, which is really good. But what it actually does is that at some point in time, the cache data gets stale. So you've gone in and updated the data source, but the cache is still holding onto old data, and then you have all these data consistency issues. So how do you actually solve this problem? The way you solve this problem is effectively, let's say you have API endpoint. You hit the API endpoint looking for data. It goes to the cache first and say, hey, do you have the data that I'm looking for? And you say, well, I don't have the data I'm looking for. So you go into the data source, get the data, and when you get the data, you chuck it back into the data cache, right? So that's okay, that's all good. So subsequent calls will always find the data in the data cache, and then it's quick, right? Now what happens is that if you want to update this data over here, the main data source, you always go through another API endpoint, or the same API endpoint, whatever it is. You go to this API endpoint, and when it updates the data in the cache, it invalidates updates the data in the data source, it invalidates the cache over here. So what it means is it removes the item from the cache. So if you're looking for the data again, when you go in, you'll find that there's no data in there, and you start from scratch. You go back to your main data source, you get the data, and so by doing this, your data isn't stale. So it's always the most recent copy that you have. You can do certain things like you can improve the performance by actually priming the cache. So when you start the application, you can actually load data from the data source and chuck it into the cache. So the first time it's not empty. So you can do things like that to improve your performance even further. The one thing that you need to think about is that most cases, sometimes the cache is a lot smaller than your actual data source. So you still need to think about, hey, what happens with, how long do I hold on to this thing? Lifetime of the cache data itself, you need to start thinking about that. You want to start thinking about data eviction policies. So if data is there in the cache for a very long time, maybe you want to get rid of it, or you need to come up with policies that handle that well. The one thing that you need to be careful of in this thing is like someone coming in directly and updating the data source over here. So in which case, then you still have the same problem that you originally started with. So you end up with stale data over here. Materialized view is the next pattern I want to talk about. When you're going and looking at data itself, right? Like I said, typically in most cases we're still storing data in a relational database. So you have multiple tables, and you do joins, you do group bys, and all these kind of things. And this is generally quite slow. The second thing is if you want to do calculated fields, I'll give an example of something from my industry, energy, right? So one of the things that we do at AGL is we have all these smart meters, right? So the smart meters basically collect usage information about the electricity that you've consumed, and they keep sending back data every 15 minutes. So you can actually look at it and say, well, hey, how much is my consumption, this hour, or this day, this week, and so on and so forth. You can actually get all the data. You can actually look at it. But here's the thing, right? So the meter data is always in units like kilowatt hours or something like that. The user doesn't understand what that unit is really. They want to know in dollar amounts how much they've actually consumed. And so there's a lot of complex calculation. So they could have like the price could be different between certain time periods, and people could be in different prices, and you need to kind of like calculate all of these in the fly. And rather than actually calculate this on the fly, what if you pre-calculated this and created a materialized view where everything resides over there? And that would actually make it really performant. So the way to fix the problem, like I said, is effectively you create separate views based on the specific queries. And you can do a whole bunch of these combined calculated fields. You can do transformations. You do all of this stuff and put it in a separate view. And so in this example, right, so you've got this complex data. You do your complex group bys and everything else and chuck it into a materialized view. And whenever you want data, you just get it directly from your materialized view. Just remember that this is a read-only view of the data itself, right? So if you want to go change the data, you still need to go and update the source data over here. So things that you need to think about is like, how do you actually deal with trigger mechanism? When you update this data, how frequently do you start to update this, and when does it get triggered, and how do you update this? You want to start thinking about storage cost blowouts. If you start to create lots and lots of materialized views, and if the data is complex and this large, and how do you deal with it? Most of the time, it's not a problem. Like I said, we do a lot of these things ourselves at AGL. So we create a lot of views. Even usage data, so usage data that's there for every 15 minutes and so on. So it all works. It's not such a big problem. Lot of cases, the materialized views are you can store it in transient stores. You can store it in a cache, and you can literally blow it away and then recreate it whenever you want. So works quite well. The one thing is when you want strong consistency, that's still a problem. You need to figure out, the materialized view there may be a bit of a lag between the time this is updated and you see the results over here. So you need to keep that in mind. It's kind of like an extension of the materialized view itself, right? Is the right, there's a bit of a mismatch between reading and writing data. But what we generally do is we kind of like run them through like a standard, like a business logic, and they all go through the same flow. And when you're writing data, what happens is you put locks on the table itself, or on the records, and that leads to locking, and it slows down the reads. And so there's kind of like this mismatch, right? So the CQRS pattern actually solves this. Now I've been talking about CQRS for a long time. And maybe about 5, 6 years ago, when I asked the question like, how many people know about this, and hardly just a few people in the audience would put their hand up. I'm going to ask the question again. How many of you have heard about this pattern and use it? Yeah. See, the nice thing about it is like I see a lot more people putting their hand up and starting to use this pattern. So how does this pattern work? Like literally, what you do is you separate out your reads, which is effectively your queries, and your commands, which is effectively your writes. And so you kind of like use the query-centric workflow, the queue-centric workflow pattern that I was talking about, right? So when you're doing your commands, your writes, you chuck it into a queue, and your command processor, your worker over here picks up this item, and it asynchronously writes to the database. And it can be a really slow operation, but you don't care, right? So it eventually makes a lot of these changes, and it writes to your data source. And then you can still do a bunch of calculations and create your materialized views over here. So when an application wants to read the data, it just goes and just goes to the query. The data is actually appropriately shaped for it. So you can actually go and say, hey, get me the data, and then takes the data, and it's so quick, and it's really performant. So even with this design, you need to, you'll have to deal with things like this eventual consistency issues that I spoke about earlier. So you still need to reckon with that. But this is a pattern that is extremely popular these days, and there are a number of things that it actually provides, right? Even when some of the nice thing about it is like even if some parts of the system actually fail, for example, let's say the command processor fails, right, and the database is not available, whatever it may be, you can still start putting items into the queue, and then when this system is up, it can actually pick it up and then process it. And you have this materialized view over here, right? So even if this system is down, you can still have your reads, and they can still continue to work. So you kind of like introduce a lot of resiliency into the architecture itself. The next pattern is the VALET key pattern that I want to talk about. And in a typical application, when you want to access data, let's say you want to access the customer data, right? So what do? You go to an API and say, hey, can you get me this customer data? It goes over to the database, it grabs the customer data, and then gives it to you, right? So the API would actually do security checks and everything else, and that's all fine. But what if you're dealing with a different kind of data? So let's say you're dealing with something like a streaming data. Let's say it's like video images or audio images, or the data itself is so big, right? It's like large documents and so on. So in this scenario, what really happens is that when you're calling the API to get the data from the data source, all it does is it goes and streams all the data, loads it up, and then it passes it back to whoever is asking for it. And it starts to consume compute and other resources and things like that. And it's probably in the long run, it's not a great way of doing it. But you also don't want the client to go directly to the data source because you want to have, you want it to be secure and so on. So the way to fix this problem, right? So you effectively the client ends up going to the cloud application and says, hey, can you please give me a token to access the data, right? So it gives a time-limited token, which actually expires. And so you go directly to the data service, and then you give the access token, and this token is actually called the VALET key. So you give the VALET key, and it says, hey, can I have the data? And then the data is directly streamed between the service and the client, and you don't have to have someone sitting in between that actually basically reads the data and passes it back. There are certain things that you want to think about in this pattern. Again, you need to kind of like manage the validity period of the key. You don't want the validity period to be too short. When it's too short, then you got to start requesting for this another VALET key again, and that's not efficient. And you don't want to make it too long either, because in that case, you have like a rogue key running around. You're worried about misuse and things like that. This is not suitable when you are doing some kind of transformation with the data itself. Let's assume, it's probably a bad example, but let's say you have, let's say like a video, right? So like a colored, and you're converting into black and white and passing through, right? That's a transformation you're doing on the fly. And those are the kind of scenarios where it's not applicable. What you should really be doing is you should be creating a copy of it in like black and white and storing it, right? Yeah. So kind of like an extension of that is the static content hosting. Now, I kept saying data patterns. Content, I also treat content as data, so in this scenario. let's say you've got a single page. So we do this at AGL. We've got an application called My Account. It's an application that allows you to self-service, right? And it's a single page app. It's written in Angular. So what does it contain? It contains HTML. It contains TypeScript, JavaScript, CSS files, images, and all those kind of things. Now, typically what happens is a lot of these things are hosted in a web server, and all the web server does is it goes and grabs the resource from your file system, reads it back, and passes it on to the client, right? That's a wastage of the web server's resources and compute and everything else, because all it's doing is it's reading, getting it, passing it back to someone else. So what if you actually served all the static content directly from, rather than actually serve it from the web server, you basically stream, you basically serve it from your storage service, things like your blob and so on. So in the case of My Account, what we're doing is we're actually directly putting it into the CDN. So that's even better. So you chuck everything into the edge servers, and because it's only HTML and CSS and things like that, you don't have to worry about things like security and things like that, right? We still run our APIs and everything else, and that's all hosted in the server. And the server side, you still need your web service to actually process that. But at least you don't waste valuable resources in just hosting static content. There are certain things that you need to think about. Obviously, your deployment model and everything else changes now, so you need to figure out how you do it. There are certain things like, when you're using, let's say you chuck all the stuff into blob storage, the URL path can look very cryptic. So how do you map it to how you do your routing and all that? You need to figure out. But it's not too complex. You can actually do that. The next pattern I want to talk about is sharding. I keep talking about this thing, right? So you're creating more and more data these days, and which is good. But when you have large data stores, you can kind of start to introduce some limitations within the system itself. Limitation in terms of storage space, your computing resources, and they're all stretched because your database is now too big. So how do you solve the problem? You solve the problem by actually splitting the data into horizontal partitions or shards, right? And then you distribute it out. And so when your application actually wants to use certain type of data, it just goes to that shard, and it's a lot more easier to process that rather than have a really large database. So things you need to think about is like what your sharding strategy is. A lot of people basically go and say, well, we're going to base it on the customer's geolocation, where they are, and then we'll shard it based on that. Some people will basically say, A to D is a shard, and then E to H is another shard, and so on and so forth. Whatever works for you, right? There's no really good rule on saying this is the right sharding technique. But you need to make sure that whatever it is, you can partition it appropriately, right? So it's kind of like equal across the multiple shards. So the data is split up equally between multiple shards. When you have shards, you want to make sure that you avoid queries that span multiple shards as well. That'll literally kill it. I mean, so you want to avoid that at all costs. Things like reference data, and they can be shared across all these. They can be duplicated and shared across all these shards. So even if you want to do things like joins and things like that, they all work quite well. Let's move on to design and implementation patterns. This is where I want to talk a lot about. You may have legacy code, legacy applications in your system, but you are now building modern cloud applications. How do they actually talk to each other and so on? What are the patterns that are involved? There are about 9 patterns, but we've already covered a couple of them. We've covered things like CQRs and the static content hosting. So we'll talk about the rest, starting with the ambassador pattern. When you want to start talking to cloud services and so on, you may want to introduce a lot of, there's a lot of cross-cutting functionality that you want to have, things like retries and circuit breaker patterns and things like, which I'll talk about in this talk. And when you have legacy applications, it's really hard to go and change these legacy applications to to build in a lot of these things in every call that it makes. So if you want to do retry logic in it, it's really hard to go and change the legacy application so that every call that it actually makes it's got retry logic in it, for example. So the way you actually fix the problem is you end up putting a proxy that sits between the legacy application and the remote service. So every time, rather than actually call the cloud service directly, you call the proxy. The proxy is effectively the ambassador, and the ambassador is effectively the proxy that handles things like retry logic, circuit breaker. If you want to do things like monitoring and logging, all of that stuff gets done over there, and then you call the remote service. Of course, it introduces things like latency overheads. You have impact of generalized server features. For example, in some cases you don't want to do retries, right? But now you're calling generalized functionality, so you're forced to use retry. So you can fix a lot of these things by having passing a context to the proxy itself. The legacy application can pass some context, so it can decide whether it wants to do things like retry and so on. This pattern is generally implemented as a sidecar pattern. I'll talk about the sidecar pattern. I'll cover that in a bit, but just something to keep in mind. When you're writing cloud applications, you kind of like greenfields, and you start from scratch, and you kind of like do your domain-driven design. You come up with this really nice, clean architecture and data models and everything else. But then they want to talk to legacy applications. And legacy applications, you have these outdated data models and protocols and everything else. And so what happens is, to talk to them, your clean model now will kind of like gets corrupted because you need to kind of like add these data fields and things like that you didn't originally want to do, right? So how do you actually protect this? So what you do is you create this anti-corruption layer that actually sits between. It's a facade that actually sits between your legacy application and your modern cloud application, right? And this still has all this clean design and everything else. But when it wants to talk to the legacy application, it calls these methods, this functionality in the anti-corruption layer. The anti-corruption layer has all the ugly bits in it, right? It does all the transformations and everything else. It converts these nice data structures into this bad data structures, if I can call it that, and then it calls these legacy applications. And the same thing can happen over here. So the anti-corruption layer literally protects this thing. It's pretty useful when you're migrating really large legacy applications into the cloud. And there's a pattern called STRANGLER pattern. We'll talk about this in a bit. And it's kind of like that will actually help you figuring out how the permanency decisions as well. Like how long does the anti-corruption layer remain, and when do you need to get rid of it, and things like that. Backend for frontends, or BFF, is a pattern that's kind of like become prominent since we've started having microservices and things like that. It's become more and more prominent. So the backend services, right? So I'll explain what it is. The backend services tend to be very generic. So you kind of like have this nice, clean domain model that exposes all your data. So you have like a customer data and so on, or your product. You kind of like build all these kind of like generic services, backend services that exposes your data. But then you have your front ends. And let's say you have a mobile front end, and the mobile front end, when it needs to go get this data, it needs to maybe it needs to make multiple calls to get the data in the shape and size that it wants to actually display it. And so on. You've got a desktop web application, it needs data in a certain format. So to fix this problem, what you do is you create a specific, you create a separate backend service for each and every front end. So in this case, you've got a BFF for a mobile application, and you have a BFF for a desktop client application. What this mobile BFF does is it can actually start to aggregate some of these services. It may call a customer service, it may call a product service. It kind of like gets all the data together, and then it shapes it in the structure and shape that it wants, and sends it back to the mobile application. This is effectively an implementation of a gateway aggregation pattern, which is effectively what the next pattern on the screen is. So the problem, this is kind of like an extension of it, right? So what happens is that there are applications that want to call multiple services to get some functionality done. So in this case, like, you want to call services A, B, C, and D. And this generates a lot of traffic. So, you got to call multiple services, but you don't need all the data that's coming out of each and every one of the services. You only want a subset of this data. So what you do is, like, if you were to do this in your client application, there's a lot of traffic that goes back and forth for very little data that you really need, right? So what you do is you create this gateway aggregator over here that aggregates all the data together and then pass it back to the application. Now, this pattern only works when the gateway the aggregation gateway sits closer to all the other services, all the downstream services. Otherwise, you still have the same problem that you originally had, right? There are certain things that you need to worry about. One is you have all these patterns like A, B, C, and D, or the downstream services. What if A, B, and C are successful, but D is not? What do you do in those kind of scenarios, right? Do you completely fail the whole service? Or do you start to, how do you handle those kind of failures? Of course, the aggregation gateway can be a bottleneck. You need to think about, single point of failure and how you address that. There's another pattern called the gateway routing pattern. Except for the term gateway in it, they're very different to the previous pattern that I spoke about. The gateway routing pattern. Think about this thing where you have multiple consumers, right, of a certain of downstream services, and it's really hard to when you have a lot of consumers and you have a lot of services. Setting up these service endpoints to cater for all of these consumers is actually quite hard. And particularly when, let's say, one of these, particularly when, let's say, one of these services actually changes, you don't want to be in a situation where you're making changes on all the consumers because this endpoint has actually changed or the structure of this has changed. You don't want to be in a position where you go and change multiple consumers. Example could be, let's say you have an email gateway over here, right? And you decide to change your email gateway provider. And so let's say, assume you have multiple consumers over there. Rather than go and make those changes in all of them, all you need to do is change the gateway router, right? And not worrying about making any changes in the consumer. Now, of course, this does kind of like introduce latency into the system. There's another level of indirection. Another level of, it needs to go through this and then go through the actual service. So there are certain things, but you kind of like balance out the advantages with the other problems that you get with it as well. The sidecar pattern this is the one that I actually mentioned about earlier. Now, this has become quite popular in the last couple of years, particularly with the rise of containers and things like that. So what is the problem that it's actually trying to fix? Let's say you take the example of you have you have a lot of cross-cutting functionality within your application. Things like retries and so on that I actually spoke about earlier, right? Now, when you have those things, what you do is you end up creating a library. So you can actually use the library, and then using the library, you make calls to your system, right? So let's assume that you create a NuGet package. It's great. With your .NET code, it all works. But what if if the application is written in Java? Suddenly, all of that becomes unusable, right? So what you end up doing is you implement and run these shared services as a separate service. Like that, and it's sitting within the same host. So you have your primary application and you have the sidecar running in a separate process within the same container, if I can call it that. And when I do this, right, so what happens is there's a bit of inter-process communication that happens between these two things. And but this can be written in a completely different language. This can be Java, this can be .NET, and it can still work. And it's kind of like resembles like a sidecar in like a motorbike, and hence the name as well. Like I said, it works really well with containers. This is the strangler pattern that I was talking about earlier. And So when we're starting to migrate these old legacy applications into new applications, right? There may be a lot of there may be other applications that want to talk to the new application that is being migrated. A lot of this doesn't happen overnight, so you kind of like need to go through a lengthy process when you're migrating your old applications to the new. So how does it work? How do the other applications work with these the application that's being migrated? So the way you do it is you create a strangler facade, and so when you first start with, right, this is your modern application, and you have this legacy application over here. You end up calling the strangler facade, and that redirects traffic depending on that knows whether it's now you need to talk to a modern application or you need to talk to the old legacy code. It decides, and then it kind of like redirects the traffic. And over a period of time, right, this gets smaller and smaller. You know, you kind of like start to strangle the legacy application, and then it eventually dies. And so all the calls end up going to the modern implementation itself. And the key thing over here is like, when do you kind of get rid of this facade? Because that kind of like adds latency into the system, right? If you design your system well, and the strangler facade is kind of like a representation of the modern application, you literally should be able to swap out the endpoints over here, and it should just work when you move all your all the workloads through. So let's quickly talk about some of the performance and scalability patterns. The good news is that if you look at the list, we've covered all these patterns. It uses cache aside, CQRS, materialized views, and so on and so forth. So we can literally kind of like skip through this thing and then go over to resiliency patterns, right? So there's about 7 in here, but again, we probably covered some of them already, like the health endpoint monitoring is already there. Load leveling is already covered, so we got about maybe 4 or 5 more patterns to go through. Let's talk about the bulkhead pattern. So what happens is that when you're hosting an application, like a cloud application, you kind of like, and there's a lot of traffic that actually comes through. And like I said, failure is imminent, right? So when you have failure, you want to make sure that you want to isolate some of this failure. And you do this through the use of bulkheads. So if you look at ships and submarines and so on, what they do is they have these bulkheads built into them. So even if there's a breach, and there's a leak or whatever it is, they can completely seal off one of these bulkheads. And although there's water that's actually coming through one, it doesn't affect the rest of the ship. So it acts in the same principle over here. So what you do is you partition your services into groups, right? And you can actually think of it like the best example to explain this is, let's say you have like a premium subscription. You have paid users, and you have like a free subscription, right? You can start to put all the paid users into a certain bulkhead, and then you have the rest in other bulkheads and so on. So even though you get a lot of traffic in the free subscriptions, that still doesn't affect anything in the premium subscription bulkhead, right? Amazon uses what they call as cells to implement bulkheads functionality. So you could have like a load balancer and your application and your data all in one cell. And there's something goes wrong, only that cell is affected. So then they deploy it across multiple cells. So each and every cell is literally a bulkhead. So failures in one cell, they're completely isolated and don't affect the failure in other cells. Retry pattern. This is probably the first pattern that I should have talked about, right? So the thing though is that, like I said, transient errors are quite common in the cloud. And so when you do get transient failures, so first thing you need to do is to check whether it is a transient failure. So if it is a transient failure, then you want to try again. And most of the times it's okay, so it'll succeed, right? But if it doesn't succeed, then you may want to wait a little bit and then try again. And so it works out quite well. So every cloud application should have a retry logic built into it. Now, there are certain things that you want to think about, right? So one is like, how many times do you try before you give up? So maybe it's not a transient error, right? So it's a more permanent error. So you need to basically have like a certain number of retries you do before you give up. And then you don't keep trying over and over again. So that's a bad thing. It's like this thing where, you call up, your partner, your spouse, or whoever, and say, want to convey an important message. You pick up the phone. I mean, you dial her number, and she's not picking it up. You may think, oh, maybe she didn't hear the phone the first time. Maybe, took a lot. Maybe it's hidden in the purse somewhere. It took her time. You literally sometimes call again, right? And you may succeed. But if she doesn't pick up the phone for the second time, you kind of like have a little bit of back off. You back off for a while, and then you call again, right? So the same thing applies over here. So exponential back off is the preferred one. So you kind of like wait for a while, and then you kind of like double it, and then you again double it, and then you wait. But what happens is that, let's assume there are a number of calls that actually come into the system, and they've all been rejected because of some kind of failure. And they all have exponential back off, and they keep hitting the server back at the same time. And suddenly, when the system is up and running, you get all these calls coming back at the same time. So what you need to do is you need to start to introduce things like jitters into your back off algorithm. So it kind of like introduces randomness into the system. So when you go back and call the service, they're not hitting the service at the same time. Extension of the retry is like the circuit breaker pattern, right? So at some point in time, you need to give up. And when you do give up, so when you do give up, so you need to stop hitting the service over and over again. So you stop. This, the circuit breaker literally is taken from, electricity in the house, right? When you have a short in the house, for example, the system trips and the circuit breaker, comes into play. So there are literally 3 states to the circuit breaker. The closed state, when current is flowing through, or all the calls are coming through, that's the closed state. That's the normal state. But when you do retry, and after a certain amount of time it actually fails, it basically triggers the circuit breaker, and it's an open state. At that point in time, current is not flowing, or calls aren't being made. But when calls aren't being made, I mean, that's not the end of it, right? So every so often, you need to go back and see if it's working again. So that's like the half-open state. So when in the half-open state, you still make a call, and the call succeeds, then you continue on. The thing about circuit breaker, right, is you should always have a fallback. That's a better way of implementing it, rather than saying, hey, you know what, the other service isn't working, I'm just going to throw up an error message, or do graceful degradation or something. And rather than that, right, you need to have a fallback. Now, the example that I give is, let's assume that you've got a road, right? You've got a main road, and all the traffic is flowing through it. But there's some kind of an accident that's happened. Rather than let more and more vehicles go through, you have kind of like you have a stop sign over there in the front, and you don't let any more vehicles go through, right? But that's not enough. You need to have a detour. So the detour may actually take you longer to get there. So in this case, right, you may want to display cache data rather than actually going to the real data source and getting the data. So, but it still continues to work. It may be a little bit slower, but I mean, hey, at least it's working, right? Or the data may be a little bit slow, stale, but it'll still work. So every now and then, you start to let a few more cars go through, right? If that car succeeds in getting through, then you can actually open the main road for all traffic, right? So you kind of like need to follow the same principle. In some cases, you may want to consider about accelerated circuit breaking. So I spoke about things like throttling. When throttling is there, you don't want to, you basically don't want to do retry. You kind of like break the circuit right away. And I'm running pretty close to my time. So just a couple of more patterns to go. A compensating transaction is when you have databases, right? One of the things the nice thing about databases is ACID in nature. So you can run everything in a transaction. You can run multiple calls, and all these calls you can commit them or roll them back at the end of the transaction, right? It's great. However, when you have distributed systems, right, and some of these could be long running, holding on to these resources in terms of a transaction is really a bad thing. So rather than actually do transactions, right, so you kind of like do inserts and do updates and things like that, and so you have compensating transactions where you kind of like undo the operation that you just did. That's a much better way. So let's say you put money into someone's account, and there's some kind of failure. You kind of like the next step is not to undo is not to kind of like you just reverse the operation. You've taken some money out, you put the money back, or you kind of like have this compensating transaction to actually do it. Much better way, and it doesn't lock up any of the resources, and you get good performance and everything else. Of course, you need to think about things like item put into consideration. If you do the same thing again, what happens? All those kind of things need to be taken into account. The scheduler agent supervisor pattern is kind of like an extension of this, right? And so when you have multiple steps that you actually perform, and so rolling back is really hard, right? So what you do is you do this by having these three. You have the scheduler, agent, and the supervisor. The scheduler is what arranges all the steps that need to be done, and the agent basically contains the logic that needs to be executed. And the supervisor basically monitors to see, hey, if there's any failure in any of the steps that's happened, right? If there's failure in any of these steps, then what it does, it actually calls the compensating transactions through the appropriate agents. And if you think, this sounds complicated, well, it is, right? It's not trivial. It's harder to implement and so on and so forth, but you do get the advantage based on that. Now, that's kind of like, it's just like, we just right on time. Let's kind of quickly recap. We do go through about 21 patterns all up. It's not that you're going to use all of these things, from day one. You got to use what is appropriate for you and so on. And, your mileage may vary, how you implement them. There's no strict rules about some of these things that are actually said. But when you do come across a situation, you at least you kind of like know enough about it to actually dig a little bit deeper. And to dig a little bit deeper, there are certain resources that you can actually use. There's a book called Cloud Architecture Patterns. It came about 5 years ago. It was written by a fellow MVP, Bill. It's actually quite a good book. And then you have this book, The Designing Distributed Systems, a more recent book that's actually come out. It talks about a whole bunch of patterns and paradigms. It even talks about things like, there's a lot of things like containers that's kind of like new now, that was not there in Bill's book. It talks about things like sidecar pattern as an example and how it all works. And there's this other book, this came out last year, Cloud Native Development Patterns and Best Practices. Again, it talks about a number of those patterns that I mentioned today in this talk, right? But one valuable resource is this thing over here, this docs.microsoft.com Azure Architecture Patterns. The structure and the grouping of the patterns and everything else I picked up from that site. It's actually it's a good resource. I would highly recommend going through that. And of course, you've got the Amazons have got their architecture website. It's got a lot of white papers in there. So highly recommend reading through those white papers. Really good. Last but not the least, if you want to implement some of those resiliency patterns, retries and bulkheads and circuit breakers and things like that, there's a library that you can actually use. It's called Poly. So again, highly recommend. In fact, there was a talk on Poly yesterday. It was the last talk yesterday. I'm not sure. Did any of you go to that one? Yeah, a few people. So again, I highly recommend looking into Poly if you want to implement these patterns. That's all I had. I mean, if you've got any questions, we've run out of time, but I'll hang around for questions. You can always email me, or that's my Twitter handle, Mahesh Krishnan. You can ask me questions on Twitter. Make sure that you fill out the feedback on the way out. Green would be good, but if you've got further feedback, I'm happy to hear as well. Right? Thanks. All right, thank you.
This is Aggie from the